Have you ever wondered why the language of numbers seems to predict the secrets of the physical world with such uncanny accuracy? We often view our search for universal truths as two grand, converging paths of human intellect. One path is a system of pure logic and abstract patterns moving through a landscape where literal meaning is secondary to consistency. The other path is firmly rooted in the physical realm, nourished by direct observation and the data of our senses. These represent the distinct worlds of mathematics and physics. While they frequently travel side by side and trade essential concepts, their origins, their goals, and their core identities remain fundamentally separate. This separation isn't just for textbooks. It is a deep conceptual divide that dictates how we interpret everything from a falling leaf to the warped fabric of the cosmos. Mathematics, at its heart, is the investigation of stable patterns built from a foundation of chosen axioms. A mathematician dwells in a territory of total abstraction. The variables and structures they manipulate, whether they are sets, groups, or complex manifolds, don't actually need to exist in the tangible world. Their validity isn't proven by experiments, but by rigid deduction from internal rules. One could build an entire logical system of geometry without ever mentioning a physical shape, simply by stating, consider a group of entities called nodes and a set of connections called paths governed by these specific laws. Math is the architecture of thought, regardless of the building's material. The true strength of mathematics is this detachment. It builds perfect logical machines that can process any information that fits their gears. This thirst for universal application defines the mathematical spirit. Why fixate on a problem in 3 dimensions when a solution for n dimensions is more robust and elegant? The generalized proof is more sophisticated because it covers a million specific scenarios with one sweeping truth. The mathematician aims to forge a master key capable of unlocking every door in the house of logic. Even if most of those doors open into rooms that have no physical counterpart, the work remains valid, guided by a compass of internal rigor and aesthetic grace. Physics, by contrast, is chained to a specific, stubborn actuality. The physicist doesn't care about every possible universe that logic could dream up. They care about this specific reality we occupy. While they utilize the logical machines built by mathematicians, they must power those machines with data that carries physical weight. For someone studying nature, a unit of measurement isn't just an abstract variable. It represents mass, the tangible resistance you feel when pushing a heavy object, or the invisible grip of gravity keeping our planet in its tracks. Symbols represent real forces, the tension in a wire, the shove of a gust of wind, or the pull of a magnet. Because of this, the physicist is intensely focused on the special case, specifically our world of 3 spatial dimensions and 1 flow of time. When a mathematician unveils a brilliant theorem for multidimensional space, the physicist immediately asks, how does this function in our 4-dimensional spacetime? This isn't a lack of vision, it is a necessary boundary. Physical reasoning is steered not just by formal proofs, but by a gut feeling for how things move, an intuition built from years of watching the world work. This instinct serves as a vital filter, highlighting which mathematical trails lead to discovery and which are just logical dead ends. The friction between these 2 approaches becomes clearest when we translate physical intuition into formal math. A physicist watches a swinging weight and feels the conflict between gravity and momentum. They map that feeling onto a set of differential equations. A mathematician can then take those equations and dissect their symmetries and stability without ever visualizing a clock or a weight. Physics uses logic to describe reality. Math uses logic to describe itself. The physicist must always return across the bridge to the real world, interpreting the math to conclude that a longer string means a slower swing, a claim you can actually test with a stopwatch. This divergence creates a different relationship with exactness. To a mathematician, total rigor is the only standard. Every logical step must be airtight.
In physics, however, that level of obsession can actually stall progress. Our world is cluttered and messy, and its laws are often first seen through simplified models. A physicist will gladly ignore air friction to understand the core of motion, or treat a massive star as a single point to simplify gravity. Demanding mathematical perfection from the start would paralyze the process of discovery. A physicist needs to be accurate enough to be right without letting the quest for precision obscure the actual phenomenon. We must realize this isn't a competition. Mathematics isn't a servant to the sciences. It is a sovereign territory of the mind. Scholars of math have every right to explore ideas based purely on beauty with no regard for practical use. History is full of useless math, like non-Euclidean geometry or group theory, that sat on a shelf for decades until it became the only language capable of describing a new physical theory. Physics is a demanding client for math, but it isn't the only one. Ultimately, the partnership between these fields is what drives modern understanding. Physics asks the heavy questions about existence, math provides the toolbox of structures to frame the answers. But the scientist must perform that final, vital act, tying the abstract symbols back to something we can measure: the tick of a sensor, the flash in a particle detector, or the shifting light of a far-off sun. Without the framework of math, physics would be a pile of random notes. Without the anchor of physics, much of math would be a beautiful but lonely game. Their relationship is a constant conversation between form and meaning, between the abstract and the concrete. To mistake one for the other is to miss the point of both. Recognizing their unique roles, one mapping the limits of reason, the other applying that reason to the stars, is the first step towards understanding the alliance that has solved the world's greatest mysteries. They're not the same path, but together they illuminate the entire human experience. This partnership succeeds because of the tension at its center. It is a productive friction. The physicist, standing on solid ground, asks the theorist, "Can your numbers explain this?" This demand stretches the math, often revealing new patterns or inspiring new fields of study. In return, the mathematician occasionally hands the physicist a tool of such immense power, like the calculus Einstein used for relativity, that it feels like discovering the universe's own mother tongue. This cycle, moving from a physical question to an abstract journey and back to a deeper truth, is the engine of all progress. It reminds us that our search for knowledge isn't a straight line, but a negotiation between the world we feel and the logic we can imagine. To stand where these two paths cross, respecting both the weight of reality and the freedom of thought, is to hold the true key to science. If you enjoyed this deep dive, please hit the like button and let us know your thoughts here at Hard Science Theory. What if the next great breakthrough is already hidden in a useless equation? Consider the sheer magnitude of our scientific history, from the early stargazers who sought order in the night sky to the modern researchers peering into the quantum foam. Every leap forward has required this delicate balance. We find ourselves living in an era where the divide between theoretical speculation and empirical evidence is thinner than ever, yet more important to define. When we discuss the architecture of the universe, we are essentially discussing how we translate our sensory experiences into the language of logic. This is why the distinction between math and physics matters so deeply. It prevents us from confusing the map for the territory. The mathematician draws the most intricate, perfect maps of every possible terrain, while the physicist is the explorer actually walking through the mud, using those maps to find the specific path that leads home. Think about the way we teach science. Often we present formulas as if they are the truth itself, but a formula is just a description. Gravity existed long before Newton wrote down the inverse square law. The planets followed their orbits without the need for Kepler's 3 laws. Our mathematical descriptions are human-made bridges built to connect our minds to the vastness of the external world. When we recognize that physics is an interpretation of reality and math is the system of rules that makes that interpretation possible, we gain a deeper appreciation for the creative.
As we look toward the future, the boundaries of these two fields continue to push each other. String theory, quantum gravity, and the study of dark energy all sit at the edge of what we can prove. In these realms, the math often gets ahead of the physical evidence. We find ourselves with beautiful, symmetrical equations that describe universes we haven't yet seen. Is it physics yet, or is it still pure math? This is the frontier. This is where the next generation of thinkers will have to navigate the gap. They will have to decide when a mathematical possibility becomes a physical reality. It is a journey that requires the courage to be wrong and the rigor to be exact. It requires us to listen to the whispers of the universe while maintaining the strict silence of logical proof. In every classroom and every laboratory, this dialogue continues. It is a testament to human curiosity that we are not satisfied with just seeing the world. We want to understand the very rules that govern it. We want to know why things are the way they are and not some other way. This drive is what brings the physicist and the mathematician together. They are two halves of the same quest. One provides the how, and the other provides the why. One gives us the tools to build, and the other gives us the reason to explore. Together, they form the most powerful alliance in human history, an alliance that has taken us from the caves to the moon and beyond. So the next time you see a complex equation on a chalkboard, don't just see numbers and symbols. See a bridge. See an attempt to capture a piece of reality and hold it still long enough for us to understand it. And the next time you look up at the stars, don't just see points of light. See the physical manifestation of those same numbers. The universe is a grand puzzle, and we are slowly putting the pieces together, using the twin lights of logic and observation to guide our way. This is the essence of the scientific endeavor. This is the beauty of the distinction. By keeping math and physics separate in our minds, we allow them to work together more effectively. We allow them to challenge each other, to refine each other, and ultimately to reveal the truth about the world we call home. This is the legacy we inherit and the path we continue to walk. Every discovery, every theorem, and every experiment is a step forward in this grand, ongoing story of human discovery. It is a story that belongs to all of us.